Sure. Thanks, Matthias, for the introduction. Good afternoon, everyone. I'm Xiaomin Ouyang from HKST. So I will be presenting the paper mentioned by Mario in his keynote this morning. So actually, in this paper, we are talking about time series foundation models ready to revolutionize predictive building analytics. So this work is a joint work with Ozan, Pengrui, Liying, Dezhi, Mario, and Mani while I was a postdoc at UCLA. So just mentioned by the previous speaker, so in building analytics, accurately forecasting key metrics such as energy consumption or in the temperature is very important. So for example, suppose if we have 84 hours of energy usage data, then how can we predict the energy consumption in the next 12 hours? So first, we humans can predict the tendency of the energy usage by ourselves based on our domain knowledges. And we can also train machine learning models to forecast this time series data. And these days, you might also think that foundation models might provide also an effective solution. So recently, foundation models have gained lots of attention due to their success in language tasks. And here, we are discussing a broader concept of foundation models, including both large language models as well as models that can process other data modalities. So the key advantage of foundation models is their strong generalization capabilities, which means they can perform zero-shot prediction without domain-specific training. And in addition to large language models, recently researchers are now also exploring time series foundation models, or we call TSFMs. And we think that these models may be also particularly suited for time series data in building analytics. However, we found that there's no comprehensive evaluations on the readiness of these time series foundation models for building analytics. So in this work, we aim to assess how we are at that point. And you might have been sleeping now, but let me show you some examples. So basically, just in the past years, we have seen a surge in the development of time series foundation models. For example, as shown in this table, some of these models, such as TimeLM, actually try to fine-tune language models for time series data based on adapters. And other models, such as Coroners and Moment model, they are trying to directly train transformers from scratch based on the time series data. However, we recognize that, just mentioned by Mary this morning, we found that many of these models do not fully meet the criterion to be considered as a true time series foundation model. For example, some of these models does not account the time series characteristics because they just treat the data as simple sequences without incorporating the timestamp information. And other models lack the foundational model aspects because they are not task agnostic. Actually, most of these models are focused on forecasting tasks. And furthermore, given the limitation that these foundation models cannot, most of these foundation models cannot handle covariance. So in this paper, we are mainly focused on univariate zero-shot forecasting tasks of these models in the context of building data. So to be more specifically, in this paper, we are actually aiming to evaluate the generalizable ability of these current time series foundation models in two aspects. So including the dataset level familiarity, which means whether this model has been exposed to the test data in model training, as well as the modality level familiarity, which means whether this model has been trained with the same data modality as test set. So for example, in this work, we consider indoor temperature and energy consumption as different modalities. And we also evaluate the performance on 3 large public datasets, including the ECOB datasets that aims for indoor temperature prediction, as well as the UCI and Smart Star datasets that are focused on the energy consumption predictions. So, however, before our evaluations, we noticed that the time series data in building analytics is often highly heterogeneous and contextual varied. For example, in some scenarios, we may only require to predict data in the next 4 hours, but in other cases, we might need to make predictions in 12 hours or even longer. However, we find that most of current time series foundation models are optimized to make predictions in a specific limit of input and output length. So in order to incorporate the variability of different time series data, we actually resample the time series data and evaluate the model performance in the 3 key factors, including different context window of input data, different horizons of output data, as well as different sampling rates. And we have also compared the performance with statistical ARIMA models. And these statistical models were trained from scratch only on a specific context window. And similarly, they were also used to make prediction on both shorter and longer durations. So in the evaluations, we first evaluate the prediction errors of different models on the UCI dataset, and we call this dataset as Seeing dataset because there are 4 time series foundation models being trained using this data, including the Moment, Kronos, Lag-Llama, and Times FM model. And here we use the red horizontal line to show the best performance of statistical model and use the blue line to show the best performance of time series foundation model. And the lower is better because we are evaluating the prediction errors. And as you can see, in this comparison of Seeing dataset, time series foundation models actually show superior performance than statistical models. And we also evaluate the performance on the Smart Star dataset, while none of these time series foundation models have seen this data before. And as you can see, in these unseen datasets, the performance gap between the time series foundation models and statistical approaches narrows significantly, which shows that on unseen data, TSFMs only have marginal performance improvement. And we also compare the performance on unseen modalities. So here we use the ecobee datasets for indoor temperature prediction because we found that none of these time series foundation models have been trained on indoor temperature data. And as expected, so since these time series foundation models have not seen this data modality before, they do not have they do not perform much better than the statistical models. So we can see that actually on unseen datasets or unseen modalities, the performance gap between time series foundation models and statistical models actually is very marginal. So based on these evaluations, we found that currently these time series foundation models cannot fully meet our needs for building analytics. So, and to further improve the performance of time series foundation models, we investigate several key features that we think that we should explore in the future for building analytics. So first, unlike language models, we found that most of current time series foundation models do not incorporate the important context information, such as the physical process, the locations, or sensor characteristics. And we think that incorporating this context information in the model input would have potential to significantly enhance the performance. And second, beyond data forecasting, we think that time series foundation models should also have the capability to handle a variety of datasets, such as anomaly detection, classification, or even high-level reasoning tasks. And finally, we found that most of current TSFMs can only handle single attributes, but we think that it's very important to explore the covariance of multiple attributes, especially in building analytics, such as indoor-outdoor temperatures, as well as solar gains, etc. So to enhance the performance of time series foundation models in these key areas, we would like to encourage the community efforts in the following areas, including the data sharing, architectural innovation, systematic benchmarking, as well as resource sharing. So that's all for the talk. So for more details, please refer to our paper and our project page. Thank you.
Thank you, Prof. Xiaomin. We have questions from the audience? Oh, yes.
Very nice presentation. Very interesting topic, and our team are still working on this. And the first question is, what do you think about in the building analytics or the load forecasting? What do you think about using the time series foundation model and using a big ASTM model trained by, for example, 1,000 of buildings? These two models, what do you think about them? And no matter in the zero shot or few shots matter to inference in the target building.
Yeah, very great questions. First, I think it depends on the definition of foundation models. For example, in my understanding, as long as your model is trained on a large set of data sets and usually in an unsupervised manner for forecasting tasks, I think in that case, that model could be named as a foundation model. So I think that's a direction, or that's a potential to developing a generalizable foundation models in building analytics. Yeah.
But the existing foundation models, they involve the knowledge. I think maybe not useful for our task. For example, they're trained by the medical or the financial data in it. So what do you think about it? Do we need to denoise this knowledge from, because they are not related to our task?
That's true. Yeah, I agree that actually a general purpose foundation models may not be useful for specific tasks such as building analytics. So we actually encourage the community, for example, to build building specific foundation models which would actually have a better performance in building related tasks. Yes, I agree there.
Thank you.
Thank you for your question.
We have time for more questions. Oh, Sami.
Hi, interesting talk. So can you please go to the slide where you have compared the model performance?
This performance? Sure.
The previous one.
Okay.
So I think both the data set, you have considered multiple buildings, I assume, right? Many buildings, right? So the RMSE is like a 300 watts, right? Is it, because different buildings, the energy consumption will be varying, right? So it's like, have you considered the normalization or something? That's one part. And this RMSE of 300 or 200, whatever it is, and the right answer, is it an acceptable range, or how far it is, deviating from the baseline?
Yeah, that's a good point. Yes, so actually in our current results, we do not normalize the results, but actually to incorporate the variability of different time series data. For example, as we mentioned before, actually this data may have different lengths of input and output data. So we actually do not normalize it, but actually incorporate combinations of different input and output lengths in the data. So this is just systematical results of this data. But I think it should be more intuitive to normalize the results. Yeah, later on. Yeah.
Okay, so there's a relevant question. So you have considered like a multiple time series foundation models, right? So these models are trained using different scale or different volume of data, right?
Yeah.
Have you seen any differences among them based on the volume of data they have been trained on?
That's a good question. To be honest, I think we don't have a very clear observation on this, because, for example, some of these models even do not expose the sources of training data they have used. So, but in general, we can see that for seeing data sets, for example, some models have have introduced the training data. For seeing data set, we found that these models performs best, but for unseen data sets, I think the performance is unpredictable. Yes, and in general, we think actually the time GPT model actually performs, I think, relatively better among these models because they can dealing with. I think they can dealing with multiple multiple attributes, and as shown in this table, the time GPT model can dealing with multiple variants as well as irregular time series. So I think currently it's a relatively better model.
Thank you.
Thank you.
Thank you, Prof.